Current is flowing in a circular coil 1 whose radius is capital R. A second coil 2 whose radius is much smaller than that of the first coil. A second coil 2 whose radius is much smaller than the first is moving with a constant velocity v along the common axis. Such that the planes of the coils remain parallel to each other. During the motion. At what distance small r? From coil 1 will the EMF induced in coil 2 be maximum? I'll read the problem again. A current is flowing in a circular coil 1 whose radius is capital R1. A second coil 2 whose radius is much smaller than that of the first is moving with a constant velocity v along the axis in such a way that the planes of the coils remain parallel to each other during the motion. At what distance from coil 1 will the EMF induced in coil 2 be maximum? How to try this? Tell me, get me the idea how to try this.
Where the magnetic field will be maximum due to the ring. That is the case where maximum.
How you proceed? What you do is, let us suppose the distance between the two is r, say. Find the field produced by the current carrying coil 1 at the location of 2. Multiply it by area, that will give you the flux. This flux linked with coil 2 is changing because it is moving. So, what is the change in the flux per unit time? d5 by dt, if you find out, that will give you the induced EMF. That EMF is found as a function of this distance r. When that EMF is maximum, differentiate, put the first differential coefficient equal to, you know that now. So, flux linked with the coil 2 is phi is equal to b dot a, which here is BA you can put because theta is 0, where B is the field produced by coil 1 at the location of coil 2, and A is the area of coil 2, correct? Now, what is the EMF induced in coil 2? It is minus d phi by dt, will you agree? Which is minus d by dt of BA. As you can see, the area is not changing. What changes is the field. So, minus A into dB by dt. B is a function of small r. R is a function of t. So you make use of function of a function rule. dB by dr into dr by dt, which is minus a. Dr by dt is velocity. No. That is the induced EMF. So the problem now reduces to finding the B. What is B at the location of coil 2? You know the formula for that. Mu naught by 4 pi 2 pi n r squared I by r squared plus small r squared raised to the power 3 by 2. Will you agree? We had derived it long back. In fact, this you can write it as, you can cut 1 2 here, okay. You write it as mu naught by 2 pi. What is this? Pi r squared ni. Pi r squared is the area of the big into number of turns in it into that is its magnetic moment. No. Where mu is the magnetic moment. So induced EMF is minus AV into d by dr of mu naught mu by 2 pi r squared plus small r squared raised to the power 3 by 2. Will you agree? In fact, if you differentiate that, you can put the final answer as you check it at home. Power 5 by 2. These are all constant. You take it out and differentiate this function, is not. In fact, this you can write it as some, these are all constants, so you can write it as some C into R by R squared plus R squared power 5 by 2. Clear? See, what do you find? As this coil approaches, the flux linked with this is increasing. So, using Lenz's law, you can find out in which direction current is induced in this. Okay. As it goes away after crossing this, as it goes away, the flux linked with it is decreasing. So, you can imagine as it approaches in which direction EMF is induced, as it goes away in the opposite direction. Now, how to find where is this induced EMF maximum? Differentiate this with respect to small r. Equate it to 0, you try it at home, you will get, you can guess, you will get at what point it will be maximum? R equal to R by 2. You can check it yourself, try it, okay. At R equal to capital R by 2, the induced EMF is maximum. You differentiate that, equate it to 0. You know that now, maximizing a function. Okay. Next problem. A square frame made of copper wire. A square frame made of copper wire. Inside the bracket you write rho equal to 1.7 into 10 to the power of minus 8 ohm meter. What is this? Resistivity. A square frame made of copper wire, rho equal to 1.7 10 to the power of minus 8 ohm meter, is placed in a magnetic field of induction 0.1 Tesla. is placed in a magnetic field of induction 0.1 Tesla. The cross-sectional area of the wire is 1 square millimeter, and the area of the frame is 25 centimeters square. And the field lines are perpendicular to the frame. What quantity of electricity will pass through the frame? When the magnetic field disappears? I'll read the problem again. A square frame made of copper wire, rho is equal to 1.7 in 10 power minus 8 ohm meter, is placed in a magnetic field of induction 0.1 Tesla. The cross-sectional area of the wire is 1 square millimeter and area of the frame is 25 centimeters square, and the field lines are perpendicular to the frame. What quantity of electricity will pass through the frame when the magnetic field disappears? How to find the quantity? EMF induced is given by this. So, what is the current? If you know this current, what is the quantity flowing for a small time dt? dq equal to I dt, which is minus 1 by r d phi by dt into dt. So, you get this. He is asking what is the quantity, that is when the flux changes from say phi 1 to phi 2 say. This is minus 1 by r phi 2 minus phi 1. Correct? So, the entire problem now reduces to finding phi 2, phi 1 and resistance. Okay. Now tell me, what is phi 2? Phi 2 is 0, because it says the fields totally disappear. So, Q is equal to phi 1 by R. Will you agree? What is phi 1? What is phi 1? Tell me. Phi 1 is B into what? B into A of the frame. Will you agree? B into A of the frame now. Okay. What is R? Rho into L by rho into L by A. Okay. You take the length of the side as some small a. Then what is L there? 4a. Will you agree? He says it is a square frame, no? So if L is the length of the side, total length of that will be 4a divided by cross-sectional area, which I have called it as AW here. Okay? This you can write it as rho into 4 into A he has not given. He has given A frame. So, root of A frame. Will you agree? root of A frame resistance divided by, so that now you can write here phi by R. R is rho for root A frame AW. Will you agree? Or this is B AW root AF divided by 4 rho. Substitute the given values. 0.1 is B. How much is AW? Cross sectional area of the wire 1 square millimeter. Convert it into meter. Then root of AF. AF he says is 25 centimeter square. Centimeter square. You must convert it into meter square divided by 4 into 1.7 into 10 to the power of minus 8. You simplify this at home, you will get the answer as 0.074. What is the unit? Coulomb. Write down a straight wire of length small l. A straight wire of length small l and resistance capital R is sliding on a rectangular loop in a uniform magnetic field applied perpendicular to the loop. The strength of the field is capital B. The sides AB and CD have resistances capital R1 and capital R2 respectively. The sides AB and CD have resistances capital R1 and capital R2 respectively. Neglecting the self-inductance of the loop, find the current in the sliding wire. Find the current in the sliding wire during its motion with a constant velocity v. I'll read the problem again. A straight wire of length L and resistance R is sliding on a rectangular loop in a uniform magnetic field applied perpendicular to the plane of the loop. The wire has the sides AB and CD have resistances capital R1 and capital R2 respectively. Neglecting self-inductance of the loop, find the current flowing in the wire during its motion with a constant velocity V. Tell me how to do this. Exactly. See, when it is sliding with a constant velocity, there is an EMF BLV induced in this. So, this acts like a battery actually, and the resistance of this is the internal resistance of the battery, correct now? So, what is the external resistance? These two are in parallel, correct? So, current is total EMF by total resistance. EMF is BLV. Total resistance in the circuit is external resistance. Will you agree? They are in parallel, plus internal resistance. This is the source of EMF which offers a resistance R. You take it as its internal resistance. So, current will be E by RT, BLV by R1, R2 by R1 plus R2 plus R. Clear? Next, a wire bent as a parabola y is equal to ax square. A wire bent as a parabola y is equal to ax squared is located in a uniform magnetic field capital B, comma B vector being perpendicular to the plane xy. B vector being perpendicular to the plane xy. At the moment t is equal to 0, a connector starts sliding along the y-axis from the apex of the parabola with a constant acceleration w, Find the EMF induced in the loop. EMF induced in the loop formed as a function of y. He says a wire bent as a parabola y is equal to ax squared is located in a uniform field B being perpendicular to the plane xy. So, you take this as x direction. There is a field applied perpendicular. The parabola is like this. Okay. At the moment t is equal to 0, a connector, a wire, starts along the y-axis. It starts from its apex and moves with a constant acceleration upwards. So, at certain time instant, let us suppose it is here. It is moving upward with a acceleration w, say. Find the EMF induced as a function of y. How do you do this? How do you do this? EMF induced is given by BLV. B we know. What is L? Say this wire may be like this. He says, what is the EMF induced? Find BLV. We don't know what is V. We don't know what is L that you need to consider to find the area of the loop. Two x. L is equal to 2x. Will you agree? Yes. L is equal to 2x. Then, how to find V? V squared is equal to U squared. It starts from the apex with starts from rest, plus 2a. Yes. Will you agree? Or this is V is equal to, therefore induced EMF is BLV, which is B into 2x into root 2WY. He wants the answer in terms of Y. So, what you should do? B into 2 into, what is X? X is root Y by A. If you simplify this, tell me what it comes to. Root Y and root Y, it is Y. B 8W by A inside the root. Correct? Follow out now how to do these kind of problems. Let's take up a slightly complicated problem. A conducting rod is bent as a parabola y equal to kx squared, where k is a constant, and it is placed in a uniform magnetic field capital B, directed perpendicular to the plane of the paper. At t is equal to 0, a connector of resistance per unit length lambda, starts sliding up the parabola with a constant acceleration small a. And the parabolic frame starts rotating. With a constant angular frequency omega about the y-axis. Find the instantaneous current induced in the rod. when the frame turns through pi by 4 radians. I'll read the problem again. A conducting rod is bent as a parabola y is equal to kx squared, where k is a constant and it is placed in a uniform magnetic field of strength capital B directed perpendicular to the plane of the paper. At t is equal to 0, a connector of resistance per unit length lambda starts sliding up on the parabola with a constant acceleration small a, and the parabolic frame starts rotating with constant angular frequency omega about the y-axis. Find the instantaneous current induced in the rod when the frame turns through pi by 4 radians. Here the complication is, here it was only simply moving up with an acceleration. Here as it moves up, the frame is rotating also. So after it rotates through pi by 4 radians, what is the instantaneous current induced? So you take this as x-axis, take this as y-axis. He has applied a field, say, perpendicular to the at certain instant. It is rotating also with an angular. Tell me how you go about. Yeah. How do you find the flux? First you have to find the area. Correct now? Find the area. When the frame has turned through an angle theta, what is the flux linked? Flux linked is B dot A, which is BA cos theta. Okay. What is that A? Area swept by that. How much is that? It's really 2x dy from 0 to y. Will you agree? Twice x dy. This you can write it as 2 into, what is x? Root y by root k, root y dy. Will you agree? Or A is 2 by root k, root y is y power 3 by 2 by 3 by 2, which you can write it as 4 y power 3 by 2 by 3 root k. Will you agree? Clear? Now, during this time, when the frame has turned through an angle theta, this bar has gone up. Okay. What is the distance it has covered in that time along the y direction? Y, use S is equal to ut plus half at squared. It starts from rest from the apex, say. So, half a t squared. Will you agree? So that now you can write phi is equal to B into A. How much is A? 4 by 3 root k into y power 3 by 2. What is y? Half a t squared power 3 by 2 into cos theta. This you can write it as b by 3 root of 2 by k a power 3 by 2 t cubed cos theta. That is phi. What is the induced EMF? How do you get it? How do you get the induced EMF? Differentiate with respect to time. So, induced EMF is E is equal to minus d phi by dt, which is differentiate this with respect to, here you can see b by 3 root 2 by k a power 3 by 2, they can be taken out. Differentiate this product. Okay, first into, of course that minus sign I have brought in, first into differential of second, differential of cos is minus sign, that minus cancels, so it becomes sin theta into d theta by, which is clear, plus that minus sign I have brought it in, inside cos theta you are differentiating now t cubed, which is 3t squared. Will you agree? Now, theta equal to omega t, correct now? So, t is equal to theta by omega. Theta he says is pi by 4 radians. Will you agree? In a time interval of pi by 4 radians, he says. Therefore, induced EMF will be, you can chuck it there, I'll take that t squared out of the bracket, 3 root 2 by k, t square, take it out, t sin theta omega minus 3 cos theta. Will you agree? Or this is b a power 3 by 2 by 3 2 by k. What is t? T is pi by 4 omega, the whole squared, inside omega t, this omega t is pi by 4, sin pi by 4 is 1 by root 2 minus 3 into cos theta is pi by 4, cos pi by 4 is again, or this you can write it as pi squared b a power 3 by 2 by 48 omega squared root 2 by k pi by 4 minus 3 into 1 by root 2. This on simplification gives you pi square b a power 3 by 2 pi minus 12 by 192 omega squared root k. That is the induced EMF. Now he is asking us to find the induced current. To get the induced current, you have to divide that EMF by resistance. Now tell me, what is resistance? Lambda is resistance per unit length into the length. This is 2 lambda. What is x there? Root of y by k, which is 2 lambda by root k, root of y. Y is half a t square, correct now? So it is a by 2 inside the root, outside the root t. This is root 2a by k lambda pi by 4 omega. So from that you can now find what is the current induced EMF by resistance, which is pi squared B a power 3 by 2 pi minus 12 root k 4 omega by 192 which on simplification gives you pi a b pi minus 12 by 48 root 2
Any superposition.
What superposition?
We know the EMF due to rotating, and we know the EMF due to the rod moving upwards. So you can't be as close to that.
Try that and see whether you get the answer and let me know. Okay? I'll rub it off. Draw this figure. Write down a conducting rod AA dash of mass small m slides without friction over two long conducting rails separated by a distance small l. Another way of saying length of the conducting rod is L. At the left end, the rails are interconnected by a resistance capital R. The system is located in a uniform magnetic field capital B applied perpendicular to the plane of the loop. At the moment t is equal to 0, the rod AA dash starts moving to the right with an initial velocity V naught. E naught. Neglecting the resistance of the rails, and of the rod AA dash, neglecting the resistance of the rails and of the rod AA dash, as well as self-inductance, find one, distance covered by the rod AA dash until it comes to rest. 2. Amount of heat generated in the resistor capital R. Amount of heat generated in the resistor capital R during this process. I'll read the problem again. A conducting rod AA dash of mass small m slides without friction over two long conducting rails separated by a distance L. At the left end, the rails are interconnected by a resistance capital R. The system is located in a uniform magnetic field perpendicular to the plane of the loop. At the moment t is equal to 0, the rod AA dash starts moving to the right with an initial velocity V0. Neglecting the resistance of the rails and the rod AA dash as well as the self-inductance, find 1. Distance covered by the rod until it comes to rest. 2. Amount of heat generated in the rod during this process. Tell me how to do this. Tell me how to do this.
Most of the rod is VI. We can find the current, the EMF is VI, we can find the current.
Yeah.
And then we can use Newton.
To find?
We can use that formula B square equal to 2E.
What he has asked? He has asked the distance it has covered before it is brought to rest.
We know the acceleration, we know the initial velocity.
You can't use the equation. Let us suppose it is moving with a velocity v, say. The EMF that is induced is, will you agree? What is the current that is flowing now? When a current flows, you know that there is a force acting. In which direction it acts, you know? How much is that force on the rod? B I L, which is B into VLV by R. Correct now? Into L, how much it is? B square L square V by R. Will you agree? This is the force acting. What is the effect of this force? To reduce the velocity. Now, Newton's law says force is equal to mass into acceleration. That should be equal to V squared L squared V by R. So, A is equal to V squared L squared V by R. Will you agree? I have written it correctly. Divide by? Is it all right now? Negative, it is deceleration. No, it's slowing down. It's not acceleration. It is not picking velocity. It is losing velocity now. Clear? Now, acceleration, it is dV by dt, but v is a function of its position. So dv by dt, acceleration which is dv by dt can be written as dv by ds into ds by dt. Will you agree? That should be equal to minus b squared L squared V by mr. ds by dt is what? As you can see, you can cancel this, integrate. It started with the velocity v0, finally it is brought to rest. It covers the distance, yes. Will you agree? If you simplify this, you get it as, so that yes, the distance it covers before it is brought to rest is clear? What is the second part here? What is the second part? What is the amount of heat generated? It's very simple, tell me. Use the law of conservation of energy and tell me. Half mv0 squared is the right answer. Because initially it has the kinetic energy, it started with a velocity v0, means it started with the kinetic energy half mv0 squared. Finally it has been brought to rest because it has been losing energy, and this energy has appeared in the form of heat. So the heat energy that appears is simply half m v0 squared. If you want, you can substitute for v0 from that formula into that. This, clear? Next. The magnetic flux through a stationary loop, with a resistance capital R, varies during a time interval tau, as phi is equal to at into tau minus t. Find the amount of heat generated in the loop during that time. Neglect the inductance of the loop. Heat generated in the loop during that time means during the interval tau. Tell me how to do this. Yes, given flux as a function of time, he says over a time tau, what is the amount of heat generated in the loop? Tell me. No, not you, somebody else. Same fellow giving the answer. Somebody else, come on. You work it out later. Tell me how to attack this. Instead of that, he has given phi. Differentiate with respect to, that will give you E. E by R will give you I. I squared RT. Here, I squared R dt, integrate it from 0 to tau. Come on, do it. First find I, which is E by R. E is given by d phi by dt, remember. rather minus d phi by dt. You use minus d phi by dt. Once you find I squared r dt. Integrate this from 0 to tau. Come on. Got the answer for the earlier problem? How much you get?
A square r into tau cube plus 4 by 3 tau cube.
Integrate that and get me the final answer.
E square tau cube by 3r.
Exactly correct. The amount of heat released is in a time tau. You get it as a square tau cubed by 3r. A square tau cubed by 3r. Got the answer? You got the answer? You find E by R, which is I squared R dt, then integrate it from 0 to tau. Got the answer? Complete it at home. Next, take this problem. A plane loop, you draw this figure, a plane loop shown in the figure, a plane loop shown in the figure is shaped as two squares. Is shaped as two squares. With the sides small a equal to 20 centimeter, with the sides small a equal to 20 centimeter and small b equal to 10 centimeter, is introduced in a uniform magnetic field at right angles to the plane of the loop. At right angles to the plane of the loop. The field varies with the time as B is equal to V naught sin omega t, where V naught equal to 10 millitesla and omega is equal to 100 per second. Find the amplitude of the current induced in the loop. Find the amplitude of the current induced in the loop if its resistance per unit length is lambda equal to 50 ohm per meter. Neglect the inductance of the coil, inductance of the loop. neglect the inductance of the loop. I'll read the problem again. A plane loop shown in the figure is shaped as two squares with sides small a equal to 20 centimeter and small b equal to 10 centimeter. Is introduced into a uniform magnetic field at right angles to the plane of the loop. The magnetic induction varies with the time as b equal to b naught sine omega t, where b naught is 10 millitesla and omega is 100 per second. Find the amplitude of the current induced in the loop if its resistance per unit length is lambda equal to 50 ohm per meter. Neglect the inductance of the loop. Come on, how will you do this? Tell me, one of you tell me.
And differentiated, negative differential is the EMF. And we can find the resistance.
Listen. First, what is the magnetic flux linked with the bigger square? I will call it phi 1. I will call this square as 1. As to what is the magnetic flux linked with the bigger square? It is B dot A, which is BA here. B is B naught sine omega t. A is A squared. Will you agree? Square, no, it is. What is the magnetic flux linked with the smaller loop? B naught B squared sine omega t. Will you agree? Okay. What is the EMF induced in the first loop? It is minus d phi 1 by dt, which is minus b naught a squared omega cos omega t. Will you agree? EMF induced in the second loop minus d phi 2 by dt, which is minus b naught b squared omega cos omega t. Will you agree? Will you agree? Now, what is the net EMF? Net EMF is even why?
If it is clockwise in the bigger, then it will be in the opposite direction.
Exactly. That's the crucial point here. The coils are so connected, the currents are flowing in the opposite direction. So remember then, the net EMF is E1 minus E2, which is omega B naught A squared minus B squared cos omega t. From this, what is the induced current? Induced current is what is the amplitude of this? Amplitude of this induced, this is of the type I is equal to I naught cos omega t. Amplitude of this is now, what is the resistance of this loop? Tell me. In terms of lambda and A and B, if you put 4 lambda into, yes. Therefore, you can put I naught is equal to omega B naught A squared minus B squared by 4 lambda A plus B. Substitute the value and get me what is I naught. 5 into 10 to the power of minus 4 you get. He gets minus 6. Check. Okay, complete it at home. Next, take this problem. A uniform magnetic field of induction capital B vector. A uniform magnetic field of induction capital B vector is changing in magnitude. Is changing in magnitude at a constant rate dB by dt. At a constant rate dB by dt. You are given a mass small m of copper. You are given a mass small m of copper, which is to be drawn into a wire of radius small r. Which is to be drawn into a wire of radius small r and formed into a circular loop of radius capital R. Into a circular loop of radius capital R. Show that the induced current in the loop does not depend on the size of the wire. Or of the loop, and is given by I is equal to m by 4 pi rho d dB by dt, where rho is the resistivity and small d is the density of copper. I'll read the problem again. A uniform magnetic field of induction B vector is changing in magnitude at a constant rate dB by dt. You are given a mass small m of copper, which is to be drawn into a wire of radius small r. Radius small r means cross-sectional radius, of course, and formed into a circular loop of radius capital R. Show that the induced current in the loop does not depend on the size of the wire or the loop, and is given by I is equal to that expression, where rho is the resistivity and d is the density of copper. How we do this? He has given a mass m of copper and he says density is d. So what is the volume? Volume of copper will be mass by density. That he says has to be drawn into a wire of cross-sectional radius small r and a circular loop of radius capital R. So this should be equal to what then? Pi r squared. A cylinder means, a thin wire is a long cylinder, no. So what is its volume? Pi r squared into 2 pi capital R. That should be equal to m by d. This is 2 pi squared r squared capital R equal to m by d. Now what is induced EMF? Induced EMF is B dot A, which is B into d by dt of B dot A, d by dt of BA, which is here the area is not changing. What changes is the field. Will you agree? This is the induced EMF. What is the resistance? Don't confuse this R, this is radius. I'll call this as R dash. What is the resistance of the circuit? Resistance of the circuit is rho, okay, into L. What is L? 2 pi capital R divided by pi R squared, which is 2 rho capital R by R squared. So what is the induced current? He is asking us to find the induced current. See, it does not depend on small r as well as capital R. I is equal to E by R. What is E? pi r square dB by dt. What is r? 2 rho r by r squared. Correct? This you can really write it as multiply by 1 pi, divide by 1 pi, pi squared small r squared capital R by 2 pi rho dB by dt. This, you see, this can be replaced by actually m by 4 pi rho d, correct now? 4 pi rho d into dB by dt. This is what you get. Clear? We worked quite a lot of problems.